So in this video, we're going to talk about capacitors in series, which is going to be almost opposite of capacitors in parallel. And so when we talk about capacitors in series, if we apply potential across a combination that is in series, all right, and so one way you can tell that it's series is one end of the capacitor, right? If you imagine charge flowing through here, let's use red. It goes through one capacitor and then it goes directly into the next, where in parallel it's split off. Here that same charge will flow through each of those capacitors on its way. So that's how you can tell if it's in series. Just like in parallel, where we knew that when they're in parallel, the sum of the charge on each capacitor is equal to the amount on the equivalent capacitor. Here, each of these capacitors will have the same charge on them. And so the reason for that is, if you think about it, if let's say we get two positives here, well, that's going to draw two negatives on the opposite side, and those two negatives are going to draw two positives on this side, and those two positives will cause two negatives on the opposite side of its plate, and those two negatives will draw two positives there, and then two negatives there. And so you have to have the same charge when the capacitors are in series. Now, again, that's different than in parallel. The other difference is where in parallel the potentials were the same as that applied across the terminals. Here, we add up these potentials, and V1 plus V2 plus V3 will equal the same potential that's applied across this potential, right? And so if V1, for example, was 3 and V2 was 4 and V3 was 5, well, I know the total V of my battery had to be 12 in this case because, again, the potential across each of these adds up to the total across the terminals there. Again, that's different than in parallel, where in parallel they have the same potential. Now, to find the equivalent capacitance, we have to use this equation here. And we just have to be mindful that it's 1 over C equivalent is equal to the sum of 1 over Ci. And so what that means is we would do 1 over C1 plus 1 over C2 plus dot 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 plus 1 over Cn. We find that, and then we would take the inverse of that to find C equivalents. Right? So this here is my C equivalent. Don't forget to take that inverse there, otherwise we're not going to get the actual capacitance. And what this will cause is, in series, your equivalent capacitance can't be any greater than the smallest capacitor. Okay, and so that's one way to check. And again, I'll repeat that in series, the equivalent capacitance can't be any larger than the smallest capacitor. And the reason that this formula works is because we know each capacitor has the same charge, so our C equivalent, so Q is equal to C equivalent times V, but I know that V, so this is V of the battery, is equal to V1 plus V2 plus V3. And since V is equal to Q over C equivalent, we have Q over C equivalent. Well, the potential across each capacitor, well, is given by Q over, since they all have the same charge, C1 plus Q over C1 plus Q over C2 plus Q over C3. And since Q's are the same for all of them, we're left with 1 over C equivalent equals 1 over the summation of the capacitors. Okay, and so it's quite different than just adding them up. Okay, so it's 1 over, and then we have to remember to take the inverse of our answer. And so let's apply that to one example. Here again, we have two capacitors that are in series. Again, if I were to have charge flow through here, it goes through C2 and then through C1. And so C1 is 20 microfarads, C2 is 5 microfarads, and our potential is 10 volts. And so for A, 1 over C equivalent will be 1 over C1 plus 1 over C2. And so 1 over C equivalent equals 1 over 20 plus 1 over 5, which is equal to 1 over 4. And so C equivalent is 4 microfarads. Okay, so again, we have to flip to get our answer. For B, now that we know C equivalent, we can find the total charge of the system. And so for B, we know Q equals C equivalent times V, and that will be equal to 4 microfarads times 10 volts, and so we get 40 microcoulombs. And this is helpful because this tells me the charge on each capacitor. Since they're in series, the charge on each capacitor is equivalent or is equal to the equivalent charge found on our equivalent capacitor. And so Q1 equals Q2 equals 40 microcoulombs. The difference will be in the potential across each one, because when I add V1 plus V2, I know I'm going to get 10 volts. And we're going to use the fact that Q1, Q2 has 40 microcoulombs. I know C equals Q over, let me restart that. I know Q is C times V, and so CV1 will be equal to Q over C1, and so that's 40 microcoulombs over C1 is 20 microfarads, and so we get 2 volts, which means I know there's going to be 8 volts across V2. V2 equals 40 microcoulombs over 5 microfarads, and I get 8 volts, and there we have it. 8 volts, 2 volts gives me the sum, 10 volts. And so that's how we work with capacitors in series.